Okay, for section 2.3, we are talking about slope and rate of change algebraically. So remember in 2.2, we define the derivative. So the derivative can be interpreted as the slope of the tangent line or the instantaneous rate of change. At a particular value for x. So given y equals f of x, the derivative of f, remember we write that as f prime of x is equal to the limit as h goes to 0. We're shrinking in that that secant line. We're getting those two x values closer and closer together. So x plus h, where that h is getting smaller and smaller, minus f of x. So that's f of x2 minus f of x1 over x2 minus x1, which would just be h. This is rise over run, it's the slope of the tangent line. So you're looking at, this is the slope between x and y1, or that's f of x, and x plus h and y2, which is f of x plus h. So y2 minus y1 over x2 minus x1, but you're letting that h value, the distance between those two x values, get closer and closer to 0. Okay. So we use different symbols to talk about the derivative. You could use the f prime of x. You could also call it y prime. You could do dy dx, the derivative of y with respect to x. D by dx of f of x. That's another way to write it. So all of these things mean the same thing, just take the derivative. So thinking about graphs, when would a function not be differentiable? And so what would have to happen for there to be no tangent line at a point? So if you had a vertical asymptote, you couldn't figure out the slope of the tangent line. So say we were looking at 1 over x. So you have this thing going on here. So this vertical asymptote causes a problem. You don't know what the derivative is there. It's not differentiable here. Say there's a vertical jump. So you have, I don't know, something like this. You wouldn't be able to guesstimate the slope there. So there is there's no tangent line, so there's no slope to that tangent line. So it's not differentiable there either. You could also look at that and see like the limit wouldn't exist at that point, right? Something else is a sharp turn. So if you're looking at the graph, this is interesting. Probably the interesting example here. So at this point right here, the point there, this is not differentiable. And that's because of you're trying to, let me see if I can do this with a red thing. So you're trying to, match the slope as you get in here closer and closer. So say you were looking at these two, this is x plus h, and you're sliding that h closer and closer to here. So the secant line on this side would be like this, and the secant line on this side would be like this, and those slopes are, opposite of one another. So the fact that those slopes aren't starting to match up, that's a problem. And so this sharp turn makes the function not differentiable there. See this, that idea of a single tangent line. This is two different tangent lines at that point, and that's a problem. Same here, right? So that's also same here. But they're, that one, the slope is undefined, and that's the problem. Okay, a whole is another instance where a function wouldn't be necessarily differentiable. So you're looking at, say, here. And then lastly, a vertical tangent. You want the function to be smooth and continuous. So these are all the ways that a function could not be smooth and continuous. This would mean that the slope is undefined. So say you have like something like this point right here, the slope there is vertical. So that slope is undefined, which would mean that the slope of the tangent line is undefined. Okay. So these are all the times when basically you want a function to be smooth and continuous, and if it's not, then you could have issues. So what we're going to do is figure out, we're going to use different techniques to figure out what the derivatives are algebraically, instead of doing the whole limit thing and trying to figure that out for everyone, because that's kind of the challenge. We're looking at the graphs for all of them or making a table. We'd like for there to be other options. So we're going to learn some rules. The first of which is the power rule. So we have this function f of x equals x to the r, where r is a real number. Then f prime of x is going to be r times x to the r minus 1. So what I like to say when I do this is exponent down front decrease it by 1. So when you are doing the derivative for x to some power, you're going to write the power in front, then decrease the power by 1. So for this one, we have f prime of x. This is the derivative, is going to be exponent down front, decrease it by 1. So 2.4 minus 1, really 2.4 x to the 1.4. For number 2, f prime of x, the derivative, is going to be exponent down front, so negative 2/5 x to the negative 2/5 minus 1. So you're looking at negative 2/5 x. That's minus 5 over 5, what, negative 7/5? Okay. Lastly, we have, I'm going to rewrite this function. So I'll do that in green. This function is x to the 1/2, right? A square root is the same thing as the power of 1/2. So f prime of x, we're going to do exponent down front, decrease it by 1. So 1/2 minus 1, so we're looking at 1/2 x to the negative 1/2. Something you can keep in mind is that those negative exponents, you could write them on the bottom. So this is like 2 times the square root of x on the bottom here. Or like in between there, 1 over 2 times x to the 1/2. When you move that exponent to the bottom, it makes it positive, or move it to the top, it makes it negative. Okay, that may come into play later, but we can move on for now. The constant multiple rule. So if you have a constant times a function, then you can basically just ignore the constant and take the derivative of f still. So when you're doing that with the power rule, if you have a constant times x to the r, it's going to be the constant times r x to the r minus 1. So exponent down front still, decrease it by 1, still just ignore that constant in front. So for this one, we have f prime of x is going to equal 3 times, this is x to the 1. So exponent down front, decrease it by 1. So that takes 1 minus 1 here. So you're looking at 3 times x to the 0, which is 1. So just 3 would be the derivative there. All right, for number 2, f prime of x equals 2 times exponent down front, so 0.8 x to the 0.8 minus 1. So 2 times 0.8, which is 1.6, x to the 0.8 minus 1 is negative 0.2. All right, let's see, how are we doing? This note packet is long. Okay, I'm going to keep going. I'll stop in a minute and then do another video, but I'm going to get through like half of this maybe. So for number 3, I'm going to rewrite this using what that rule I was just talking about. When an exponent is on the bottom, you can write it on the top with a negative exponent. So this 4 over x to the 5th is the same thing as 4 times x to the negative 5th. So what I'm going to do now is take the derivative. So f prime of x equals, leave that constant alone, exponent down front, decrease it by 1. So I have negative 20 multiplying these two things, x to the negative 6. And if I wanted to simplify that, I could write that as negative 20 over x to the 6, but I don't need to. For number 4, we can do a similar thing, rewriting this function. We have negative 1 over x to the 1/3, that the cubed root is a 1/3 power, or you can write this as negative 1 times x to the negative 1/3. So for the derivative, f prime of x, you would do that negative 1 times exponent down front, decrease it by 1, 3, minus 1. So you have those negatives cancel, you have just 1/3, x to the negative 4/3. I'm probably going to leave that alone, but you could push that to the bottom if you wanted to. Okay, talking about the derivative of a constant. So if you have like y equals, I don't know, 3, think about that. What would the slope of the tangent line be? It's flat, so the slope is 0. And that's the derivative of a constant. So think about that with like arithmetic, you have c times x to the 0. That would be your constant, right? Anything y equals c, that would be c times x to the 0. So actually, let me change this to c. So if you were taking the derivative, you would leave that constant alone, do exponent down front, decrease it by 1. So times x to the 0 minus 1. So that would just be 0 because of this 0. So the derivative is 0. Okay. So if f and g are both differentiable functions, and y is the sum or difference of those two functions, then the derivative you can just do in pieces too. Is f prime of x plus or minus whichever it is, g prime of x. So you can just do it in pieces. Y equals 3. Oh, I didn't mean to use this example already, but y prime is 0. It's a constant, so the slope of the tangent line is 0. Number 2, looking at 2x plus 1, y prime. This is like f, and this is g. So we can take the derivative of those pieces. So the derivative of 2x would be 2 times x, exponent down front, sorry. This is x to the 1. We have exponent down front, decrease it by 1, and then plus the derivative of that constant is 0. The constant being, should I make these different colors? Maybe that would be easier. Let's do this. Make that green. Make this green. Okay. So then simplifying, we have 2 times x to the 0. So just 2 plus 0, which is just 2. All right, and on number 3, we actually have 3 functions, f, g, and h, say, but you can do the derivative of each one of those separate from the other. So f prime of x is going to be 2 times exponent down front, decrease it by 1, minus exponent down front, decrease it by 1, plus 0, because that's the derivative of that constant, 7. So this is 4 times x minus just 1/3, because that would be x to the 0 plus 0. Okay. And then let's see, we have these 3 functions here. So exponent down front, decrease it by 1. Exponent down front, decrease it by 1. This is the same thing as 2x to the negative 1. So exponent down front, decrease it by 1. So we have 3 times x squared plus 8 halves is 4, x to the negative 1/2, and then minus 2x to the negative 2. Okay, so go back and watch any of that again, like pause it, try to catch up, try to figure out where I got what, and then let me know if you need any help with it. So I am going to show you how to do some of these. Let's do 1 and 4. Let's just do 1 and 4, and the other ones you could do later. But so do we have the tools to find the derivative of f of x equals x squared plus x squared times x plus 1? The answer is yes. Distribute this first, and then we can. So f of x is equal to, well, now I can't tell what those are. But x cubed then plus x squared, and then do the derivative. So f prime of x would be 3x squared, exponent down front, decrease it by 1, plus 2x to the first, exponent down front, decrease it by 1. I'll teach you a different way to do that as well, but I'll do that in a different video. So our number 1, we could FOIL first, right? So this would be the same thing as 2x squared. So first outer would be minus 3x, inner plus 2x, and last would be minus 3. Simplify that again, you get 2x squared minus x minus 3, and then take a derivative. Y prime would be exponent down front, so 2 times 2 times x to the first, exponent down front, decrease it by 1, minus the exponent down front, so that would be a 1x to the 0, because that's the x to the first, right? So exponent down front, decrease it by 1, and then the derivative of the constant is 0. So 4x minus 1. And again, I'll show you how to do that differently soon. Let's see. How much do I want to get into? Okay, let's do number 4, and then I believe I'm going to take a break, and then I'll do the rest of this packet on a different video. So we are looking at here, if we were to simplify this, this would be x to the 4th over x squared plus 5x cubed over x squared. That would be x squared plus 5x. And then we want to take the derivative of that. So f prime of x, the exponent down front, decrease it by 1, plus exponent down front, decrease it by 1. So you're looking at 2x plus 5. Yes, we will pause there and come back later.